Okay, there's one last comment I want to make about electric flux, and that is related to a question that some of you have asked in your reading reflections, is why doesn't a charge outside of a surface contribute to the flux? So let's look at an example where I have maybe a positive and a negative and maybe another positive charge, and I put them all inside of a Gaussian surface. And then the question is, why wouldn't a charge out here, let's say it's a positive charge out here, why wouldn't that charge contribute to the flux through this surface? Um, your book goes through a detailed proof of this, and I just want to give you a quick heuristic explanation, just so you can kind of get the picture. If I draw the field lines, if I just focus on this charge for a second, and I draw the field lines due to this charge, remember they all come out radially from the charge. Okay, so what I'd like you to observe here is that notice for every line that enters the surface, like this one, it also leaves the surface. And the same here, and here, and so on. Every line that enters the surface also leaves the surface. If I divide this surface up into pieces, you can see that this piece is bigger than this piece, and the increase in area just perfectly balances the decrease in field strength as we go from here to here. Okay, so this is a very heuristic argument. The mathematical details are in your textbook. The same thing is true even if you have a more complex electric field pattern. Okay, if I draw, I didn't put arrows on my field lines, but if I draw a Gaussian surface anywhere, actually, wherever I like, if I put it, say, here, you see that I have the same behavior, that for every line that enters, it leaves. So the net flux through the surface is zero because there's no charges contained inside. The charges all are outside, and these charges outside do not contribute to the flux through the surface. So Gauss's law states that the electric flux through a closed surface is proportional to the amount of charge that's enclosed by the surface. Okay, so if I have zero charge enclosed, then the net flux, this is the net, through the surface is zero. And there's some work that needs to be done here in order to figure out, first of all, to prove this proportionality and to find the constant of proportionality. So again, I refer you to your textbook for all of that. And I'm just going to write down the results. So we've already found the formula for the electric flux in my previous lecture. And it looks like this. E dot N dA integrated over the entire surface. So that's the flux. And then the right-hand side is the charge enclosed, and there's a constant of proportionality. That constant ends up being 1 over epsilon naught. So that's a pretty simple relation, a direct proportion between the flux and the enclosed charge. Okay, so I want to show a few applications of Gauss's law. The most obvious one, and the one that we've basically been talking about so far, is that if I can calculate the electric flux through a closed surface, I can use that to conclude how much charge is enclosed by that surface. But we can also do this in the reverse direction. Maybe I know what the charge distribution in space looks like, and I want to know what does the electric field due to that charge look like. So sometimes I may know the right-hand side, and I can use that to compute the left-hand side, which will then give me a formula for the electric field. Okay, so I want to do a couple of examples like that. So the first application is, what if I have a uniformly charged disk or plate? The first time we did it for a disk, but it's the same result if we do it for any shape of plate. So maybe it has a charge density on it, which remember we called sigma. And the question is, what is the electric field here at some point near the plate, say a distance r from the plate? So what if we want to know the electric field here? Now, we did this for the disk. If you recall, we broke this up into a bunch of rings, and we used the Biot-Savart law first on each piece of the ring, and integrated that over the entire ring to get the electric field due to one ring, and then we integrated that over all rings to get the electric field due to the entire plate. Okay, so that was a complicated calculation that had multiple steps that involved integration. So Gauss's law actually makes this calculation much simpler. So I have this charged plate. Sigma, by the way, the charge density is the total charge on the plate divided by the area of the plate. So it's a density in the sense that it's a quantity per area. It's an area density. And so here's the point in question, and I want to know what's the electric field at this point. So I'm going to draw a Gaussian surface. Remember, Gaussian surface is a mathematical surface. It's not a physical surface, and we can choose it however we like. And what we should see in the end is that any property of the Gaussian surface that we chose should not appear in our final equation, because the physical world doesn't care what mathematical imaginary surface we chose. So it should not appear in the final answer. So I'm going to choose a Gaussian surface, and choosing the shape of the surface comes with a little bit of practice to develop some intuition. But I'm going to do a rectangular box. It's going to be my Gaussian surface. And this point that's in question is going to be right on the surface. And the reason for that is because when we calculate the flux to the surface, we're going to be talking about the electric field where it pierces the surface. So that's the electric field that we'll be able to solve for using Gauss's law. So if this box goes through the sheet here and comes out the other side. Okay, so here's my Gaussian surface. It's this rectangular box that includes a piece of this charged plate, a rectangular piece of this charged plate. So that's the only charge that is contained inside this box, is this piece of our uniformly charged sheet. So let's say this box has an area A box, not to be confused with the area of the sheet, which I'll call A sheet. And then the question is, what is the charge enclosed by this box? Well, if sigma is the charge per area, and I know what the area of this rectangle is, the area of this rectangle is the same as the area of this rectangle. So it's A box. Then I can use sigma to find the amount of charge that's enclosed, because this is an area times a charge per area. And then I know what sigma is equal to. It's Q over A sheet. So this is the fraction of the sheet that's enclosed by my box times the total charge on the sheet should give me the fraction of charge, the total charge that's enclosed by the box. Okay, now we need to find the flux, the electric flux through this surface, this box-shaped surface. And this is where we have to use a little bit of prior knowledge about electric fields. In this case, we know that the electric field points directly away from the sheet if it's positively charged. Okay, so the electric field on the surface of my box here is pointing away. Here it's pointing away. Up here, it's pointing away. And we're using an argument from symmetry, where we're going to say that the electric field here at this point is going to be the same as the electric field here at this point, because these are the same distance from the sheet. So by symmetry, we expect the electric field to be the same on each side. So if this one's a distance r from the sheet, then this one's a distance r from the sheet. Okay, so now we can calculate the flux. We need to know the normals. So the normal on this surface is going to point parallel to the electric field. The normal on this surface is parallel to the electric field. The normal up here is perpendicular to the electric field, so we know that that dot product is going to be 0. Down here, perpendicular on the face that is coming, if we have a normal that's coming at us out of the near side face, that's also perpendicular to E. Okay, so I think you see the pattern here is that the electric flux through all these different faces is 0, except for this right face and this left face. And that was the reason why this shape of Gaussian surface was chosen, because it simplifies things. So what is the flux through this surface? Which is going to be E in cosine theta times A. And theta is 0 because these are parallel, and cosine of 0 is 1. And the length of a unit vector is 1. So the flux through this right-hand surface, so let me call this phi right, is just the electric field magnitude times the area of that face, which I called A box. And then over here, I think it's pretty simple to see that if I were to write this all out for the left face, I get the same thing. I have E is parallel to N hat, and so this is theta is going to be 0. Cosine theta is 1. The length of N hat is 1, and so we end up with E A box. So the total flux is the sum of these two. So now we can write down Gauss's law. So the total flux, electric flux through the surface, phi E, is 2 times E times the area of the face of the box. And that's equal to 1 over epsilon naught times the charge enclosed. The charge enclosed was A box over A sheet times Q. And then I need to multiply by 1 over epsilon naught. All right, and so we see right away the area of the box cancels, which is what I had alluded to earlier. This must happen because this box is imaginary. So the physical behavior can't depend on this imaginary box. And then if I solve this for E, I have 1/2, and then Q over A sheet, I can write that as sigma again over epsilon naught. And this is exactly the same formula we found using the Biot-Savart law, which required a lot more work. I did this in about half a page, most of which was a drawing. The Biot-Savart was a much longer calculation. So Gauss's law makes some calculations easier, but only if we already know something about the symmetry of the situation, like I did here. And I already knew the electric field direction was always going to be away from the sheet. As long as we're not close to the edge up here, it's going to be pointed away from the sheet. So if you know a little bit about the shape and pattern of your electric field and any symmetries, then Gauss's law is an easy way to find the electric field due to a charge. Okay, so application number 2. Remember that we said that the electric field inside a conductor, when it's at equilibrium, is equal to 0. And the reason for that is because if the electric field wasn't 0, so I'm going to do a quick proof by contradiction here. If E was not 0, then charges would be moving following the electric field lines. And if the charges are moving, then we are not in equilibrium. Okay, so it's a proof by contradiction. So therefore, we conclude that the electric field inside a conductor, if it's in equilibrium, must be 0. Otherwise, charges would be moving and it wouldn't be in equilibrium. Now, another thing that we've said about conductors is that excess charge in a conductor, then any net charge has to accumulate on the surface of the conductor. Okay, so I'm going to use Gauss's law to verify this second conclusion here. Okay, so I'm going to use Gauss's law to verify this. Okay, so let's say I have a maybe oddly shaped conductor here, and I'm going to draw a Gaussian surface inside this conductor. So maybe I'll just draw like a circle or a spherical Gaussian surface inside the conductor. And I ask, how much charge is contained inside of my Gaussian surface? Well, we know from Gauss's law that the flux through the surface is equal to the charge enclosed by the surface over epsilon naught. But we know something about the flux already. We know that E, everywhere inside a conductor, if it's in equilibrium, is 0. So that means that the electric field at all points on this Gaussian surface is 0. Therefore, the flux through this surface must be 0. So the flux is 0, and that shows us right away that the charge enclosed must be 0. And I think it's fairly straightforward to see that I can draw any Gaussian surface, and this is going to be true inside the conductor, including one that is just barely inside the conductor, but basically encompasses its entire interior. Okay, if that's my Gaussian surface, if I'm just inside the conductor, just inside the edge, the electric field is still 0 on the surface. So its flux is 0 through the surface, and therefore the charge contained in the surface is 0. Okay, so any net charge in a conductor that's in equilibrium does not live inside. It has to gather on the outside edge, on the surface of the conductor. Okay, and the third application of Gauss's law that I'd like to do, and this is the last one I'm going to do in this video, is finding the E field due to a spherical charge distribution. So you may recall earlier in the semester, we used the Biot-Savart law on a situation like this to find that the electric field at the center of this spherical charge distribution, assuming it's a uniformly distributed charge here, the electric field at the center here is 0. And that was a rather hard calculation because we had to use the Biot-Savart law on every piece of the sphere to figure out what its contribution is to the electric field here and integrate over the entire sphere. Okay, so Gauss's law is going to make this job much easier. So let me draw my Gaussian surface like this for a second. Okay. Now, this is a hollow sphere. So the charge enclosed by this Gaussian surface is 0. And if the charge enclosed is 0, then the flux through the surface must be 0. So A is definitely not 0 of my surface, so E must be 0. So everywhere along this surface, E is 0. Now, if I draw a smaller surface, I get the same result. No charge enclosed, no electric field on the surface. And it's plain to see that that would happen no matter which surface I chose, no matter how small or how large. And so even if I get down to an infinitesimally small surface, I can show very easily, without really doing much of a calculation at all, that the electric field everywhere inside of this spherical charge distribution is 0. Okay, the next thing I'd like to try here is let's look at a Gaussian surface that is inside of this shell. Okay, so it's a shell. The Gaussian surface is a shell that fits in between the inner radius and the outer radius of this thick shell that I've drawn here. Now we know that if this is a conductor, So let me add that this is a conductor. I should have said that before. It didn't affect what we did just now, but it's important now. If this is a conductor, then I know that the electric field everywhere on this surface is 0. Okay, and so the flux through this surface, E equals 0. Therefore, the flux through the surface is 0. Therefore, the charge enclosed by the surface is 0. And so what we've concluded here is that no charge will accumulate on the inside. Even though there's a net charge on this spherical conductor, none of it will accumulate on the inside surface. Because if it did, we wouldn't have 0 electric field inside the conductor. Okay, and then the last example I want to draw is if I put a Gaussian surface outside of the sphere that encompasses the whole sphere. And let's say that this surface has a radius r. And let's say that this total charge here, the net charge on the surface here, on the spherical shell, is Q. And so now let's use Gauss's law on this sphere to find what the electric field strength is anywhere on this sphere. Okay, so the charge enclosed is the easy part, right? The charge enclosed is just the total charge. So it's all of the charge that's enclosed by this biggest sphere that I've drawn, and that's just going to be the net charge that is on the outside of this spherical shell here. So the charge enclosed is Q, which is positive. Okay, and then the flux. All right, so here's the flux, the integral over the entire surface, E dot n dA. Now, we do know something about the electric field here that we're going to use, which is that the electric field must be spherically symmetric due to this charge distribution. We saw that before when we were using the Biot-Savart law a few chapters ago. So I know at this point, for example, that the electric field must point radially, like that. And that's true on all points of this surface, okay, all the way around. And what about n hat? Well, n hat is the normal to the surface. Well, the normal to a spherical surface is also pointing directly out, radially. So this simplifies the math quite a bit. I have E dot n. Is this going to be E, right? Because E dot n is E n hat cos theta. Cos theta is 0 because they're parallel. So this is 1. The length of a unit vector is 1. So E dot n is just the strength of the magnetic field. Electric field. And notice that also by the symmetry argument, if each of these points is a distance r away from the center, then they would each have the same electric field strength. So E is effectively a constant everywhere on this surface. Okay, so again, we're using some knowledge about what the electric field symmetries are in order to use Gauss's law. If we don't know anything, or if we have a situation where there aren't any symmetries or patterns that we can take advantage of, then Gauss's law is not very useful, actually. So I've just argued here that this integral E dot n becomes just the magnitude of E dA. And then I argued that E is constant everywhere on the surface because every point on the surface is equally distant from the center. So I can pull a constant out of my integral. And I just have the integral over the surface, over the entire surface of dA, which is going to be E times the area of the surface, which in this case, the surface is a sphere, E times 4 pi r squared. All right, so that's the flux. The charge enclosed is Q, and so the last step is to write Gauss's law. So Gauss's law says that the electric flux is equal to the charge enclosed over epsilon naught. The electric flux we just found is E times 4 pi r squared. The charge enclosed is capital Q. And then if I solve this for E, I have 1 over 4 pi epsilon naught Q over r squared. And we recognize this formula. This is the exact same formula that we were using at the beginning of the semester for the electric field due to a point charge. 1 over 4 pi epsilon naught is the constant K that we'd been using. And we have the charge over distance squared. So outside of a spherical shell of charge, the electric field behaves like it would for a point charge if the point charge were centered inside the sphere. Okay, so out here, the electric field is the same as for a point charge. Inside this material, this conducting material, the electric field is 0. And we use that to conclude that no charge can accumulate on the inside surface. No net charge can accumulate there. So the net charge has to be 0. And then we also concluded that everywhere inside of this sphere, the electric field is 0. Okay, so all three of those were applications of Gauss's law.